السلام عليكم شباب. Yesterday we discussed the rectifier, which is AC to DC, and we presented a video to show how to design that type of converters, right? Today we will take another topic, which is DC to DC. And DC to DC choppers are very important, especially in renewable energy, to harness or to get the output from low DC voltage from the solar panels, and then to boost it up or change it to the suitable value of voltage that you need it in order either to convert it to AC later using inverter or to charge a battery. So today we will talk about that part, and as we discussed last time, there's three main basic circuits of DC to DC converter. The first one is buck, which means that step down the voltage, buck choppers or buck converters. And the second one is boost, which is step up the value of the voltage. And there is another one, it can operate in both sides. It can boost up or step up the voltage, and it can step it down, which is buck boost circuit or converter. Today, before I go through this one, I would like to show you, I just implemented that circuit like that one, to show you how we can convert it from DC to another DC. So I made a circuit like this, for example, a battery, and then this battery connected to a transistor, NPN transistor, and then to a DC motor, as you can see on that set just right now, and then back to this side. Okay, and then here I need to control this signal in order to get the another value of DC. So if we look at this one, by the way, you can buy this one from the engineering village, or you can get it online and you can refer to that code. This is the name, basic electricity, which is, you can go to that one and you can buy it directly from Amazon or any company, so you can get those. You can do lots of experiments, especially basic experiments, to learn how to deal with circuits, and maybe you need it later for your kids.
How much is it?
I think I bought it about 1.5 years ago. It cost me about 80 riyals, something like this, 86 riyals. I cannot remember exactly. But it's helpful, especially for the children, or to those who just would like to learn electricity or simple circuits, and then they can later develop their own experiment. So it is good for the basics to start with those. So in this one, I just built that circuit, and if you look at that, now I have the transistor. If I control this one, sending a current signal to that NPN transistor. See here, if I just keep this signal on, sorry, so if you keep the signal on, that means I'm sending a signal to this gate, which is a current signal. See that? The motors rotate, right? Now, if I just would like to control its speed, suppose that if I send a signal like those, unfortunately I cannot do it here because I don't have a controller right now. So, but if you make like pulse width modulation signal here, a signal which is turn on and turn off, this switch, that means you can control your speed. So let's look at that speed of that motor. So if you look at the fan, if I just put it like this, now high speed, right? If I try to make it like this, like that signal, but mechanically only by my hand manually, I can get lower speeds, right? Yeah, it's not constant because I'm just doing it with low frequency first, and the second one it's just manual. And in addition to that, there is no filter with this one. That means the speed, you'll see that a little bit a change in the speed. See, you can control the speed. So if you just make a circuit here that can make that signal, you can control your pulse width, and then you can get different speeds. And this one, it can be applied for electrical car with the same application. You can look at that one. This example, you can use it for electrical car. The DC motor can rotate the car and can move, and then what you need only, you control these pulses. So when you press the button, that means you change the duty cycle or the time on and off of each period of your frequency. So this is, for example, this is the signal which is sent to this one. So if I assume this is the on time, T on, and this is the off, this is the whole period, and this is the off time here. So if I change T off, so if I make this one smaller, the T on, and make the T off larger, the speed will decrease. If I press more, that means I'm increasing this time, so that means I'm increasing the duty cycle. Duty cycle can be related like this, K equal T on over the total period, which is that one. So as you increase this ratio, that means you increase in this one, and then you can increase the speed. So this is one of that application. You can use it to control the speed of the car. So you can speed up, speed down, see, with the same application, like those. Now, if we go to the pulse width modulation itself, how we can create those? Actually, we can create them by two signals, which is a carrier signal and reference signal. So that one, I can make it like this one. I will take one signal which is constant, like a DC value, which is known as the reference signal. And then with another signal which is carrier, you can create it, you can program it on a system, and then you can get that one. Sorry, this is the triangle, so you can put it in another sheet. This is your reference signal, which is a DC, and then if you bring a triangle signal like this, or a pseudo signals, and then this is the carrier one, and then connect them to a comparator. So the comparator will compare between those two signals. This is comparator, and then you can get that output. Example, if you have this signal, and the comparator will compare between two signals like this. So if, for example, if this one is higher, if the signal of the carrier is higher than the signal of the reference, that means you will get on time like this. Okay, and then if this one, if the carrier higher than the reference, you will get 0 for this time, and so on. So you will get signals like this, and you can continue like that. Now, if you would like to change the duty cycle, the on time and off, you can shift this one up and down, the DC value, right, which is the reference. So if you shift it up, that means the turn on become wider and the turn off become lower, right, or thinner. So you can, and the same thing, if you go down, that means the turn off will be wider and you can go to up to 0. So the duty cycle, if we look at that, the relation is, as we said, K equal T on over T the period. So that means it can be ranged from 0 till 1, right? When T on equal T, you will get 1. So the range of this one from K, it is between 0 and 1. So now this one you can apply it for different circuits, like the buck, the boost, and the buck boost. You can apply the same principle in order to change the duty cycle. Again, just to remind you that duty cycle will be used to turn on and turn off the transistor. So the signal will be sent to the gate of the transistor or to the switch. Is it clear, Shara? Let's go to the circuits. So if we go to the first one, which is the buck, let's go first through the slides. So I will start by introduction, then talk about buck converter, boost converter, and then buck boost converter. So this is the importance of converters or DC to DC converters in the term of solar system and in the solar systems. So harnessing solar energy using photovoltaics. Also, it could be useful for fuel cell energy storages, batteries to charge those batteries. Require DC to DC converters, and to operate this system optimally, DC to DC converters are required. So whenever you go to a system with solar system, you will find those type of converters. So here's an example about that one. This is Solar Explorer kit. It is from Texas Instrument. You can buy that one. It's good for teaching based, and it can be, this is one full system. It can be used to charge the battery. You can use it as inverter to convert your power to AC. So this is one full set, and we will talk about it with the next slide. So if we look at the system, or the solar system actually, the characteristics of the cells or solar cells, okay, they are not actually, they change the relation between the power and the voltage. It changes with the time due to the radiation, due to the temperature, due to the weather effects. So different characteristics in every time depending on those entities. So if we look at here, for example, we might see this characteristic, we might find it in the morning, and we might find that one in the noon time, where the solar or the sun at the middle of the, okay, in the noon time in the sky. So you get that one. So if you see that the maximum power, so this is the power, right, and this is the voltage, right? So the maximum power, for example, at that time should be this point. But for example, at 2 or 3, you might see it here. And the same thing in the morning time, about 11, it could be here. Okay, so the maximum power, I need to operate my system in optimal, right? I need to get maximum power from those, not just to operate those solar system just to get the power and that's it. I need to get as much as I can, so I need to operate it at maximum point. So I need my operation to be at this point. Therefore, in order to operate this during each time, I need to use buck boost converters to get that to reach to this point in order to harness the maximum power from the solar cell. Okay, so buck boost converter is there. Again, to charge the battery, there is another application. So the battery, for example, if you get here, for example, this is 12 volt, right? And it could be also 24 or 30, depends on the battery, right? So suppose that you have here higher value and you need again to change it, or this one is fluctuating. So definitely you need the value of the voltage to be here fixed in order to charge the battery with the same value of voltage, right? So therefore you need another DC to DC converter. And the same thing in the other side here, in order to feed this one, to feed this inverter, which is DC to AC, to convert it to AC, okay, power, you need another DC to DC boost. In order, if you have low voltage to this side, you need to boost it up in order to fit the required output voltage in your system. So you can see those applications. To be honest, this is the typical design for this solar kit, but you will find in the market different designs. You might just find one or two, depend on the type of the circuit which is designed for. But this is what's explained here is just a kit which is made by Texas Instruments. And this is how you can see that one. It's arranged like this one. If you look at here, this one DC to DC boost, which is used to get the maximum power point tracking, and which is that one. And then there is another one to charge the battery, which is same one here. And there is another one here, DC to DC where is the other one? DC to DC, yeah, that one. Also, it can be used to step up the voltage and then send it to this one in order to convert it to AC. Is it clear? So this is a good example to show the application of those DC to DC converters. And as I told you before, also in the solar car, you need those in order to control the speed. So DC to DC converter, as we discussed it, it is step down, which is buck converter, step up, which is boost converter, it can step up the voltage, and step down, step up, which is buck boost converters. And the first one is buck converter. Buck, as we said, it's step down voltage, but it's step up the current, because we assume that the power in the input approximately, we cannot say 100% exactly, but approximately, if I assume that the input power should be equal to output power, definitely if I step up the voltage, if I step down the voltage, the current will go higher, right? Yeah. So this is the circuit actually. If you look at this one, it's approximately same as this one. Same as this one, basically. But what is added here? A filter on the side. If you look at that, and there is an inductor here, and a capacitor, which is like a low pass filter, right? To get out of those ribbons, so you will get smooth output DC. So if you have a filter like this one, and then you start to just label this duty cycle here, the filter will take care of those noise. So you will not see that the speed is changing like this, fluctuating. You will see it's a smooth speed. Okay, fixed speed. So this is how it looks like. So, and the operation of that one. So if you look into this circuit, actually you will play with this switch, or you will change this switch either to be on or off. So in on state, the circuit will look like this, and in off state, the circuit will look like that. So if you look at the first one here and you trace the red curve, when it is on, the current will flow from here to the inductor and to the capacitor and some to the load, right? So so they charge this area, and then later, once you turn it off, now there is no current on this side. But if you look at here, there is some charge stored over this area, right? So this charge will be released like this, so the current will continue like that one through the diode and then free, right, through that diode. So this is like a freewheeling diode, make that continuous current. So in the on time, the energy will come from this side, and when it is off, the energy will be supplied from that side. So in both, but you will see that this is just only temporary source, right, which is the inductor. So it will goes down until it reach again until the next turn on comes like that one. So it will be on and off, so that will charge and discharge in each cycle. Remember that this one, it should be operated with high frequency, okay, in order to get that one, not in the line frequency, which is 50 Hz. No, it should be high frequency. So this is the signal which should turn on and turn on that transistors. And if we look at to the output from that one, we can simulate this one a little bit. So I will explain through the simulation. Let's go to the PC. Here's, so let's open the circuit. So for this is the back circuit. If we look at it, as we said, that how we create the pulse width modulation, this is how we create the pulse width modulation. If you want to show you this one, I will show you. This is, I call this one reference, V reference, as you can see it, and that one V carrier. And this is where the output signal which should go to the transistor. So let's run that one and see first this one. So here, let's run. So I need V reference and then V carrier. So this is a sawtooth, you can see it. Now see here, it's in this one. Now this is your carrier, right? And this one your reference. Your reference at 0.5, and this one it's alternate between 0 and 1. So from this interval, from here till here in this interval, definitely the reference is higher, right? So it will be on. So there is a signal will be sent to the switch. In the second side, which is that from this interval, from here, from this point till the here, go to the switch. On for some time and off for another time. Now, if I change my reference, for example, if I would like to increase the duty cycle, which is key, that means I need to raise up that DC value. So if I go to here, for example, if I change it from 0.5, if I make it, for example, 0.8, okay, you will see that, see now, the on time is longer than the off time, right? So now you will get higher value of duty cycle, which is 0.8 in this case, and so on. So now let's go to the next part from the simulation. So let's put this one back now to 0.5. Okay. Now, if we look at this one, exactly what you see, exactly like the circuit which I showed it to here with that one. The only extra thing here is the voltage and the current probe in order to test the current and the voltage in different places. So this is probes for the currents and voltages. Okay, this is the main circuit with the diode and the filter and the load. Okay, so the carrier frequency, which is here, you see it's 20K, it's too high, not 50 Hz. Okay, and then I have inductor with this value 1 millihenry, and the capacitor, this is the load 5 ohm, and this is 47 microfarad capacitor. And those filters should be also it should be designed well when you design those, not just put the values randomly. You need to know what is your carrier signal, and also you need, because you need to get those rebels out, right? You need to smooth your output, and also you need to consider like what we had seen yesterday in the video. Okay, on that video, if the load is changing, you have to consider that. So you have to consider those impacts. So if we go to this one now, the relation between the input and the output for the buck, it is like this. V output equal K, which is the duty cycle, multiplied by Bs. So if I'm looking to that one, which I have it here, it is 0.5 and this one 1 to 1, so I will get 0.5, which is the rebel, right? So my K is the duty cycle is 0.5. Therefore, if I put here 50, definitely I will get output of 25 in this side, right? So the output, it will be 25. We can run that one and see the output. There is a small rebel, you can see it's 0.04, which is very, very small. So if you, for example, if you just zoom out, so you will see that it's pure DC. You can approximate it pure DC. So look at that one here. Let's look at the scale here. Just started from 24.94. Okay, so it's very, very small. So if we look at that one, just change that one. If I put it to 0 and then that one to 20 to 30, you will see just a line. It's line, right? It's a pure DC, which is 25. Now that means I converted my signal from my input from 50 volt to 25 volt. If you increase the duty cycle, definitely you will get higher value, right? If you decrease it, you will get lower value. For example, if I go to 0.8, which we have seen it right just minutes ago, so let's look at that one. Run the simulation and see the output. See now, you have about 40 volts because our duty cycle is 0.8. So to play with duty cycle will show that the voltage can increase and can decrease, but it's a step down in this case. So the maximum you can go is 50 when your duty cycle is 1, right? And the lower you can go up to 0. Definitely, if you would like to trace the currents inside those, for example, what is the current here, what is the voltage in this place? This switch will turn on and turn off, right? So when this switch turn on, okay, that means the current will go through this side. So the voltage here exactly equal the voltage across the source. And when this switch, which is the transistor, switch off, the voltage across to that, now your current in that case, it is on this loop, right, which is here. And that means this is a diode, right? And the diode connects the current from this point to this point, right? So that means like a short, so the voltage will appear 0 across this one, right? So you can check it, you can test it if you would like to see the details inside that one. So you can test it. You can see that VA, see that when it is on, it's there and it is off. Now, if you look at that one here, now if you ignore this part and just look at that, the signal which is here, it is 50 and then 0. This one will go through this one. You can test that filter and you can see the output from that filter. So you can test step by step and you will see this one. Now, definitely if you have like that signal here, definitely when it goes to the inductor, it will be integrated, right? So you will see that output here across L. Let's see that. Let's see the current here. So let's get the current. So run the simulation and see the current across R. So you see. Now this is the current, right? Because it passed through the inductor, right? And now this current with this shape will go through this path here until it reaches this node, right? In this node, this current will have two paths, this path and this path, right? So two paths at that node. So if we look at to this one, what's this? It's a capacitor, right? It's a capacitor, and the other side is a resistance. So if I have like that ripples of current, okay, that means it has high frequency ripples inside that one, and a DC. If I'm looking to this one, that current which is entering to that node here, IL, that one, okay. This current, which is in the slide, is that one, okay. So this current now, if you look at it, it has a DC shift. Look at here, it's between 7.8 and 8.2, so it has a DC component, right, plus ripples. So if analyze this one by FFT, which is fast Fourier transform, we can see those components. We can press that one and you can see the components. Let me zoom around the lower frequency. So our frequency is 20K, right? So let's zoom around that one. 20. So let's take it 40K. See here, the component which is, I have a DC component which is 8 ampere. In addition to that, this ripples here. This is a ripple of 2000 kilo, but it has very small value, right? And then another one in 4000. If I just zoom it out to 6000 kilo or something, I can see it's very small ripples. Now I need to get rid of those ripples, and then I need this DC value to bear. So this DC value will go through this direction, and the ripples will go through the capacitor. And why is that? Because it's a capacitor, right? So what is the capacitor? If you look at the XL of the capacitor, it depends on the frequency. With the high frequency, so it will suck that one. And then the DC part will go to this side, right? So let's look at those. You can trace that one. Now we blocked. Let's go to the time domain. Now this is the plot before it enters the capacitor, right? The path and then path of the load or the resistance. Now if I add the other two, I will see this. Let's go to, this is IC. See now, the ripples, this ripple, which is this ripple, now it passed through the capacitor, and the DC, where is IR or iLoad? Let me check the name of that one. This is I/O. Yeah, I output. So let's add it here. See that it's almost 8, right? It is 8. Definitely with the small ribbons, but it's 8 volts, right? 8 ampere. And the ripples pass through the capacitor path. So, and now if you have a resistive load, you have 8. So if you multiply by the value of the resistor, you will see that this is your output voltage. Is it clear, Shabab? So this is how it works. So let's now look at the video and see that video of this one.
Today I'm going to teach you about buck converters and show you how to make a switch mode power supply that can work with input voltages between 8 and 30 volts, and it steps the output down to 5 volts. It can supply 3 amps continuously, and it can handle peak currents of up to 5 amps for several minutes. Let's start with why we need switch mode power supplies in the first place. In previous videos, I talked about linear voltage regulators like the LM7805 and LM317. These are really easy to use, but they're very inefficient at high voltages. For example, if you try to power a linear voltage regulator with 28 volts and had 5 volts and 3 amps on the output, you'd end up with 69 watts of heat produced, and that might cause a few problems with your circuit. For high-powered projects, you want to be using what is called a switch mode power supply. There are many different types of switch mode power supplies that can get you from one voltage to another, but today we're going to talk about buck converters, which is a type of supply that can step higher voltages down to lower voltages. Let's start with an input voltage of 10 volts, and let's put a switch in series with it. It doesn't matter what the switch is. It could be a bipolar transistor, a MOSFET, or even a crackhead mashing a mechanical switch. For efficiency reasons, you should use a MOSFET, but let's just use a generic switch symbol for now. Next, let's control the switch with a high-frequency pulse width modulated signal with a duty cycle of 50%. This will give us a square wave that's 10 volts half the time and 0 volts half the time. Now let's add an LC low-pass filter. The inductor resists sudden changes in current, and the capacitor resists sudden changes in voltage. The combined effect is that our LC low-pass filter averages out the square wave, and we get 5 volts of relatively steady DC on the output. Now, unfortunately, if you build this in real life, this will happen. But why? Well, let's say the switch is closed, and our power supply is delivering some current. This means that current is flowing through this inductor. Now let's open the switch. Since current in an inductor cannot instantly change, this means that current is still flowing through the inductor, but this side of the inductor isn't connected to anything. So you get this huge mass of electrons building up here, creating a massive negative voltage spike. This voltage spike can reach hundreds or even thousands of volts, enough to blow up any switch you connect here. If you want more detail about this phenomenon, check out my video on inductive spiking. In that video, you'll learn that the solution to the problem is to add a diode. With the diode in place, now whenever you open the switch, current can flow in a nice complete path, and the voltage after the switch barely goes below 0. This is the classic buck converter configuration, and you can use this basic circuit to step high DC voltages down to lower DC voltages in a much more efficient way than linear regulators. Now, in school, they might tell you that this formula will give you the duty cycle you need to get the output voltage you want. Unfortunately, in the real world, this is garbage. As soon as you start drawing a few amps from your power supply, the various non-ideal parts of the circuit will complicate things. You'll get power losses in your switch, your diode, and your inductor, and even your wires. It's also highly unlikely that your output current will stay exactly the same. The more current your load draws, the more the voltage will drop. So what we need is a system that can continually monitor the output voltage and adjust the pulse width accordingly. If you draw more current on the output and the output voltage drops too low, increase the pulse width. If the output voltage gets too high, decrease the pulse width. And we have to do this within a fraction of a second, otherwise we could fry the thing we're trying to power. In other words, we need a closed-loop control scheme with negative feedback. We can accomplish this by adding a feedback resistor network at the output, a ramp oscillator, and an error amplifier, we're also going to need a precision voltage reference and a suitable slope Okay, how about we make things easy? Texas Instruments has a portfolio of products called Simple Switchers. All the Simple Switcher products are practically idiot-proof, and all you have to do is add a diode, an inductor, and some capacitors. They take care of the complicated control electronics inside the chip. Let's use the adjustable version of the LM2678, and here's the circuit diagram. On the input, we have a large electrolytic capacitor in parallel with a ceramic capacitor, and this is necessary to ensure that the LM2678 can easily switch current from the input at very high speeds. If you don't have sufficient capacitance on the input, the parasitic inductance of your input power wires will limit the amount of current you can switch in every switching cycle, and the regulator just won't work. For the diode, when you're designing switch mode power supplies, you almost always want to use Schottky diodes. These have a lower forward voltage than regular silicon diodes, so they produce less heat, which is something you always have to worry about when you're working with high currents. I'll put links to the components in the video description section. This is a bootstrap capacitor, and it's used to help drive the switching transistor inside the LM2678. It can be 10 to 100 nanofarads, and it should be a ceramic capacitor with at least a 50-volt rating. On the output, we have a combination of capacitors that will smooth out the high-frequency content of the switching waveform, leaving you with relatively clean and stable DC. These resistors configure the LM2678 to give you a 5-volt output. Try to use 1% resistors if you want an accurate 5-volt output. Alright, let's build this thing. You don't want to use a breadboard for this. Use perf board or make your own PCB. Solder in the LM2678 first, leaving a large amount of space around it to fit the other components. Solder in the input electrolytic capacitor within a centimeter or two of the controller, and use short, thick lines of solder to make the connections. Do the same with the diode and the output capacitor. Keep the component leads as short as possible. When you solder the feedback resistors, try to keep the wire going back to the chip as short as possible. The layout on the underside of the board is even more important than the top side. Notice how my ground is one continuous straight line, and I arranged all the components on the top side around this. I also soldered on a ground wire for oscilloscope probing later. And look how I soldered the ceramic input and boost capacitors directly across the pins of the LM2678. If these caps are even a few millimeters away from the chip, everything will perform a lot worse. Okay, now that everything's soldered up, I'm going to power my buck converter with 10 volts, and I'm going to use my programmable electronic load to see how it performs delivering different amounts of current. If you're doing this at home, you can just use 5 ohm 10 watt power resistors as a dummy load. First, let's check the output voltage is what we want it to be. And it is. Perfect 5 volts DC. Excellent. Now let's take a look at this node in the circuit, which is called the switching node. This is before the LC low-pass filter. You can see our familiar 0 to 10 volt square wave, and the switching frequency is 250 kHz. But you can see the duty cycle is about 52% instead of the theoretical 50%. This is with a half amp load on the supply. If I increase the load to 3 amps, the duty cycle increases to 56%. And at 5 amps, the power losses are significant enough that the controller had to change the duty cycle to 61% to maintain the regulated 5-volt output. Remember when I said we were getting a perfect 5 volts? I lied. Let's change the coupling on the oscilloscope to AC coupling and zoom in. You can see that there's a small AC component on the output because our low-pass filter isn't perfect. We call this the output ripple of the power supply because it looks like little wave ripples. We have about 20 millivolts of ripple and noise with a 3 amp load. If I increase the load to 5 amps, things get noisier. If I increase the input voltage to 28 volts, the ripple waveform gets bigger and it changes shape. Ideally, we want this ripple to be as small as possible. For most applications, under 100 millivolts peak to peak will be fine, but in general, you don't want to use switch mode power supplies to power sensitive circuits like radio receivers. If you want to learn more about measuring power supply ripple, enable video annotations and check out Dave Jones's excellent video on the subject. Now let's measure the efficiency of our supply, and compare it to a linear voltage regulator. From a 28 volt input, my bench power supply is supplying 0.61 amps to our DC to DC converter. My multimeter says the output of the converter is 5.019 volts, and I have the load set to exactly 3 amps. If you're doing this at home with resistors as a load, make sure you use your multimeter to accurately measure the output current. Here's the equation for power supply efficiency. Plugging in the values we measured earlier, we find that our power supply is around 88% efficient, which is pretty good. This is why people usually use switch mode power supplies for currents higher than 1 amp. Alright, now you know how to make a high current power supply, and knowing is half the battle. Thank you for watching, and if you like this video, please check out the video description section to see how you can support me. Make sure you check out Patreon, which is kind of like an ongoing Kickstarter campaign to help fund the channel.
Any question? Is it clear? So the basic circuit of the buck is that one, and then adding the filter with the diode, and in order to free the charge while the switch is off, right? So now let's go to the next one, which is the boost circuit. Here, before we go to the boost, just we will talk about the pulse width modulation, how we can create it. So the relation between V out and the back, which is equal V output equal KVS, and then this is the relation. So you can see that this relation, which is K equal T on over T, that means it's a function of frequency, right? So this one, it can be, while VA is a function of T on and frequency, that means you can control it by 2 ways. Either by keep constant frequency operation or variable frequency operation. So if you keep the frequency, you are working like pulse width modulation, just you change the width, but the frequency is same. But if you change the frequency, also you can change the output. But the problem with the frequency, you have a filter, right? And if you have a filter, you will face a problem if the frequency is changing. So it is recommended to operate with pulse width modulation rather than to operate the system or your back with variable frequency operation. So VA is linear, and the relation is equal T on over T. So pulse width modulation more popular, as I said, because it will not affect your filter design compared to the frequency variation. Boost converter, again another circuit. It used to step up the voltage and step down the current. This is the basic circuit of boost converter. So if you look at that one now, the difference between this one, that in the buck converter, the switch was on this side, right near the source, and the inductor was here, right? And this diode was here, right? The only change of those components. Okay, so this, and now the operation of this one, if you look at when this switch is on, okay, let's go to the slide. When this switch is on, this is the circuit, the current path, right? So this source is charging this inductor, right? And if you look at also in the other side, if you assume that this capacitor is fully charged from previous cycles, so while this one is on, this capacitor is also feeding this load, right? And the current cannot go to this side because of this diode. So there is two operation. If you assume that there is a charge on this one, huh?
Yes.
Okay, so definitely this capacitor will charge. The current will go like this. When it reach here, the current cannot go to this side because it's blocked by the diode. So the current will flow to this and will feed that one during on state of this switch. Once you turn it off, now the path of the current, now this is a source, right? And there was a charge here, so you can assume it like two sources, one of them permanent and the other one is temporary, right? So that means there's high voltage here, and this one the energy which is here and here will be sent through that to the load side, and then again you will see that the ripples will go through that capacitor and the output DC to this side. Okay, so this is how it works. So let's look at the simulation to discuss those ripples and those outputs and the relation between the output and the input. So V input, which is over V out, equal 1 minus K, which is the duty cycle. So let's look at the circuit of the boost converter. So this is the circuit. Again, I'm using pulse width modulation to control that one, and then this is the inductor and this is the capacitor. By the way, the capacitor just to add the current emitter. Don't confuse with this connections. So let's start with that one. So I have a voltage source with 12 volts, and if I make it 0.5, what will be the output? Can you calculate it? Vs over, you can calculate it, right? Vs for the boost Vs over Vo equal 1 minus K, right? And you have Vs, which is, you have 12 volt, right? And you use Vo, and the duty cycle is 0.5, right? What? So that means 0.5 Vo equal 12. Right? So Vo will equal 12 over 0.5. So it will get 24 volts, right? So I'm expecting to get 24 volts. So let's run that one and see the output. V output. Let's put V output. Here's that one. Output here. This is V output. And where is the input? This is the source. So we can see both. See, this is your input, which is 12 volt, and this is your output with 24 volts with a little bit rebel depending on your design of L and C, right? So if you increase C, you will see lower rebel in the voltage. So if we look at this circuit, again you can trace the current, the voltage in each component, and you can see the value in each place, how the current looks like, and then you will understand. For example, if I trace the current which is through the diode here, I can see this current. The diode, where is the diode? So this is how the current looks like across the diode. And why is that? If you look at the circuit here, once you turn on this one, the current will go through that path, right? Therefore, you will see zero current passing through the diode, right? This zero. And then when you turn it on, this one, turn it off, the current will go from this side toward So the voltage which is here 12, it will go through, so the current will go through that one here, through this inductor, and then makes this shape, so the voltage, so the current will start to decrease until again next cycle. You can see this one. Because the energy from inductor decreases, right? So the current decreases, like so. Now this shape of current will pass through this diode toward the capacitor. When it reaches the capacitor, again, if you look at that one, it has a DC shift, a DC plus ripples, right? So the ripples directly will go through the capacitor, and the DC output will go through the. And why is that? If you look at the, for example, if you look at the relation with XC of the capacitor, it is equal 1 over 2 by F, right? FC, right? So with the value of high frequency, XC will be low, right? So the capacitor will see low XC. That means the current, the ripples current will pass through that one, right? And for the DC one, the DC here will see high impedance, right? So the current of the DC will not pass through the capacitor, right? It will pass through the DC. This is why. Yeah, you can look at that one. This is the current which is coming. This is the shape of that current, right? Which is coming from this side, and then when it reaches this node, there is two batteries. One is towards the load, and the other one toward the capacitor. The ripple, it has high ripple frequency. This ripple frequency will go through the capacitor because they will see low impedance. But the DC, it will see that capacitor as high impedance, so it will not pass through that one. It will pass through the resistance. And the same principle you can apply it for the previous one with the buck converter. The ripples will pass through that one because of that impedance, XC. So we can see this one now. This is ripple plus DC, right? Now let's plot I capacitor. See that the ripple itself only went through the capacitor. See now it's between positive and negative, right? So between 0 here. So this is the ripples. And what's the left? The DC. The DC will pass through the load or the resistor, exactly. Where is the resistor current, which is I load, right? I out, yeah, that one. See that it has just very low ripple, which is that one. So you will get that. You can see very low ripple, right? 0.0236 and 0.024, and the average approximately 0.23. If you multiply by the value of the resistance, you can get that output voltage. Is it clear, sir? Yeah. So now, if you change again the duty cycle, you can get different output voltage. For example, V out. Now it reached about 60, right? 60 volt when I make 80. So my output is about 60 volts. And if I make it, for example, 0.3, I will get lower value of voltage, right? But higher than 12 because I am using the boost converter. We can put both of them in same case, the input and the output. This is the output and the switch. You can see it's higher. So this is 12 volt and you have 17. So you can get different value of voltage and higher than your input voltage by using this type of circuits. Now let's look at a video.
In a previous video, I showed you how to make a DC to DC converter that can step down voltage. Today I'm going to show you a new circuit that can step up voltage. It's kind of like a joule thief, except a million times better. It's called a boost converter, and this one can take input voltages as low as 4 volts and step it up to 30 volts, and you can adjust the output to whatever you want. This video builds upon material that I covered in my buck converter and inductor tutorials, so make sure you watch those first if you have any questions. Let's begin with the classic boost converter schematic. Normally you'd use a transistor for the switch here, but let's keep it simple with a switch symbol. If we start with the switch open, current from our 10 volt source will flow through the inductor, through the diode, and charge up the output capacitor. There will be a small voltage drop across the diode, let's say half a volt, so the output capacitor gets charged to 9.5 volts. So far we're dropping voltage, but that's going to change soon. Next, let's close the switch. The diode prevents the capacitor from discharging, so the output stays at 9.5 volts. But now we have a current path from the input, through the inductor, straight to ground. If we keep the switch closed like this, we'd basically be short-circuiting the input through the inductor. Holy! Inductors don't like it when you do that. So we're not going to do that. We're only going to close the switch for a fraction of a second. We're going to close the switch just long enough for some current to start flowing through the inductor. When we do this, we're storing energy in the inductor in the form of a magnetic field. Now that we have some current flowing through the inductor, and therefore we have some energy stored in the inductor, we're going to quickly open the switch. Since current in inductors can't instantly change, current has to flow through the inductor, through the diode and into the output capacitor. So energy gets transferred from the inductor to the output capacitor, and the voltage increases. Our boost converter has now boosted the voltage. Now, as I said earlier, we don't want to be closing the switch for very long. We want to be controlling the switch with a high-frequency pulse-width modulated square wave. And from watching previous videos, you can guess that by increasing the pulse width, we can increase the output voltage. But how do you predict what the output voltage will be? Well, in textbooks you will often see this equation. But this equation will only work for very low currents. In the real world, the output voltage you get will be a function of your duty cycle, your inductance value, your switching frequency, your output current, and many more things. So just like with our buck converter, if we want to build a real-life boost converter, we need a controller chip that will adjust the pulse width to make sure we have a constantly regulated output voltage. Let's use the LT1370HV from Linear Technology, and as usual I'll put links in the video description section. The input and output of the supply have a combination of electrolytic and ceramic capacitance to help deal with the high-frequency currents. You're going to see this in nearly every switch mode power supply. We're going to use a Schottky diode with as low a forward voltage as possible to keep things efficient. And here we've got our feedback resistor network that I calculated to give you guys a maximum output of around 30 volts. Depending on the tolerances of your resistors and potentiometer, you may get a slightly different maximum. Now here's something new. These components are used for control loop frequency compensation. Basically, they help the controller adapt to small changes in the output voltage, giving you a cleaner DC output. Learning how to design compensation circuits requires a lot of complicated math and knowledge of control theory, which is beyond the scope of this tutorial, but here are a few links to some information. The good news is that most of the time you can just use the recommended values in your controller's datasheet and your circuit will work. Alright, let's build this thing. Start by soldering the heat-sinked controller chip onto some perf board or make your own PCB. Leave plenty of space for the other components. Keep component leads short and your solder traces thick. Add the inductor, the diode, and the capacitors. Next, add the feedback resistors, keeping things as short as possible. Finally, solder the frequency compensation components near the input and leave pins 3 and 6 unconnected. Let's look at the bottom side of the board. Notice how I arranged the components so that I could have a simple continuous ground from the input to the output. And I've soldered the ceramic input capacitor directly across the controller's input pins, and the output ceramic is in parallel with the output electrolytic. Now, if we power it up, we can take our input voltage and step it up to 30 volts. Now let's talk about the limitations of this design. It can only deliver about 50 watts before things get uncomfortably hot. You should also be aware that it has an input current limit of 5 amps. Notice how I said input current limit, not output current limit. Check this out. Let's say our converter has an output voltage of 12 volts and an output current of 1 amp, so we're delivering 12 watts of power. When I power it from a 5 volt source, it's drawing 2.78 amps. So the input current is higher than the output current, and this is because we can't just create power out of nowhere. In order to get the extra voltage on the output, we're drawing more current on the input. Overall, our boost converter is roughly 86% efficient. Finally, be careful! For safety reasons, I've limited the design of this circuit to a 30 volt output, and even just 30 volts from a large capacitor can do some damage. If you build a boost converter incorrectly, or you handle it carelessly, you could electrocute yourself.
Don't do that.
With great power electronics comes great responsibility. Thanks for watching, and if you enjoyed this video, please check out the video description section to see how you can support the channel.
So for the buck converter, so this is the relation. This is the relation of the boost converter, V over Vs equal 1 over 1 minus K. If you look at that, when if K goes to 1, that means this is infinity, right? This is theoretically it goes to infinity, but practically no, because of the parallelistic capacitance across the across open switch would bring it down. So you will see that the voltage go down a little bit. Practically, when you go to up to K equal 1. The second or the third circuit, which is buck boost converter, this is the circuit. Again, there is just manipulation of the component in order to get the same components. The capacitor at the same location. The switch now, it will return back like buck converter, but the inductor is located here, okay? And the diode is inverted to the other side. This is the difference if you look at it, just manipulation on the components. And now, again, there is 2 states to operate that one, either on state or off state, and this is, we can see this one on this 2 circuits here. When the switch is on, this source is charging this inductor, right? And while this one is charging this inductor, in the other side, this capacitor is discharging toward the load. So the current is going to this direction or passing through this direction and this loop here. Therefore, the direction of this, it's the opposite direction of the previous 2. So you will get the opposite voltage. For example, if you have you will get the opposite polarity voltage in the negative. So you have to consider that one. So for the off state, when the switch is off, definitely there is a high charge here. This one should be also discharged. So that's this discharge, which is energy, which is here, will makes the current go through this loop and will charge again the capacitor, and some will go to the load and again pass through this diode, right? So this is the main principle of the circuit. Now, we can test this one through the simulation, and the relation between this compared to VO over Vs equal K over 1 minus K. Okay, so this one, it can be obtained from this figure, but because of the short time we cannot write those. So this is the relation, and if, for example, if the K equal 0.5 here, you get 0.5 over 1 minus 0.5, so 0.5 over 0.5 you will get 1. So if the duty cycle is exactly 0.5, that means the input will equal the output. If the duty cycle higher than 0.5, the output voltage will be high, step up like the boost. If it is lower than 0.5, the value of the output voltage will be lower than the input voltage. Therefore, it works like buck converter or step down converter. So let's look at to the circuit for the simulation. Let's go to the buck boost one. Again, I'm using pulse width modulation, and this is the circuit, and my input is now 6 volts, and my duty cycle, I can make it first 0.5 in order to see that the input equal the output, and this is the circuit. So let's run and see the output. V in, this one V in, and this is V, and this is V out. See that you have 6, and you get -6, right? So you get what you have V in the input, you will get in the output, because the duty cycle is 0.5. The only thing is, it is the polarity of this output is changed, or the opposite polarity of the output voltage. Now, if we change this one to, for example, to 0.7, definitely I will get it. It will work like a boost, so the voltage will step up. See that you still have 6 in the input, but now it's about minus 14 volts, right? About minus 14 volts. The same thing if I go and select a duty cycle less than 0.5, for example 0.3, I will get lower than 6 volt. I'm expecting that. V in and V out. You see it's less than, it's about 2 point something, 2.8 or something like that. So you can get different value of voltages from that 6 volt. Okay. Is it clear? By the way, those type of circuits that just operate in one quadrant. There is another type of circuit that can do DC to DC converters, and it can work in different quadrants. It could be up to 4 quadrants. So that means for the DC machine, when you have DC machine, definitely when it operates, sometimes when it stores energy inside the inductors, right? And once you need to stop it, there's some energy should back to the source side. Therefore, you need to operate it in different quadrant. Here, just this is an example that just one quadrant type of DC to DC converter, which is known as type A of converters. And you can trace this one. The same thing, you can see that the voltage across the capacitor, this current which is across the inductor, and then this across that inductor. So when this current passes through this one, definitely the ripples will go through this capacitor, and the DC will pass through that resistance. And the comparison between, if you compare between those, this is the duty cycle in the x-axis and the voltage in the y-axis, and you can see that for the buck converter you need to, if you operate from 0 to 1 of the duty cycle, the value of the voltage increasing until it reach 1. You cannot go beyond 1, which is input equal output at this point. But for the back, the lowest point when the k equals 0, you will get 1, right? And then once you start to increase the duty cycle, you will get higher value. For the buck boost, 0.5 is V in equal V output, and from this point you can go up and down depending on the duty cycle. So we can notice those. Notice that the only that the buck converter shows a linear relation, but the other two, they don't have that linear relation. The buck boost can reduce or increase the voltage ratio with unit gain for duty cycle ratio of 50%. So this is where the trade-off. Any question? So this is the end of this lecture. Unfortunately, I don't have a YouTube for this one for the time, but if you need, I can supply later. Thank you very much.